Nuclear fusion is in the news everywhere. It's often described as energy source of the future, clean, safe, and virtually limitless. But what exactly is fusion? And if we have known about it for decades, why aren't we powering our cities with it already? Fusion is the process that powers the sun. When two nuclei, in our case deuterium and tritium, combine to form helium, it releases a neutron which carries huge amounts of energy. Fusion is built around two main approaches: magnetic confinement fusion and inertial confinement fusion. For decades, the pursuit of electricity production through fusion has primarily focused on magnetic confinement, using machines such as Tokamaks and stellarators. Within these devices, plasma must be confined to sustain the extreme conditions which are required for fusion, one of which is temperatures reaching nearly more than 100 million degrees. No material can touch that, so we need something to hold that in place. Achieving that can depend on many factors, but above all, on strong magnetic fields produced by highly sophisticated electromagnetic systems. So I'm here at the TCB Tokamak in Switzerland, where scientists study plasma shaping and stability. So what you see behind me are these huge copper electromagnets surrounding the vacuum vessel. They create fields of about 1.45 Tesla at the plasma, which is about hundreds and thousands of times stronger than the Earth's magnetic field. It is enough to study the plasma dynamics, but if we talk about future fusion power plants, this much field is not at all enough. We need much stronger fields. At first, the solution seems obvious: just make bigger copper magnets. But copper has resistance, and if we push more current through it, it heats up a lot due to Joule heating, wasting enormous energies. So at the scale needed for power production, this solution seems impractical. So the question is, what should we use instead? Wouldn't it be great if the resistance magically disappears from the conductors and we make magnet out of it? That's where superconductors come in. These are materials, when cooled below its critical temperature, carry electrical current with essentially zero resistance. That means enormous currents without wasting a lot of energy. But this isn't enough. A superconducting magnet should also survive huge currents and intense magnetic fields without losing its superconducting state. I am at the SPC facility in Willigen, and what you see here are these ITER conductors made of niobium-3 tin, which is a low-temperature superconductor. Experimental projects such as the ITER, which is currently under development in the south of France, uses niobium-3 tin conductors to make coils which provide peak field of about 10 to 12 Tesla at the winding pack and 5 to 6 Tesla at the plasma axis. But when we shift our focus from an experimental reactor to a fusion power plant, things change. Such a commercial reactor must be compact and also economically viable. One of the ways to shrink the reactor size without sacrificing its performance is through using even stronger magnetic fields. That is where low-temperature superconductors face practical limits. As the field goes higher, their critical current density starts to decrease. But high-temperature superconductors change that. Superconducting magnets made of HTS have very large current densities and can thus provide much stronger fields of nearly 20 Tesla or even more. What you see here is a YBCO tape and HTS tape. At first glance, this looks like an ordinary metal tape, but almost everything you can see is a stabilizer. The actual superconducting layer is almost about 1 micron thick. This tape has gained a lot of attention in the last few years, and most of the HTS cables and coils getting produced are made from these conductor tapes. But before these cables go into a coil, they must be tested. Behind me is the SULTAN facility in Switzerland, where superconducting cables and coils are pushed to their limits in liquid helium, huge currents, background fields of about 11.9 Tesla. Most of the conductors and cables produced in the world have been validated here. With such potential of HTS, next-generation fusion companies such as the Proxima Fusion, Commonwealth Fusion Systems, and many more are building their fusion devices utilizing HTS coils with the hope that stronger fields can bring fusion closer to reality. Fusion is not only a triumph of physics and engineering, it's a triumph of persistence, of imagination, and of believing that impossible problems are worth tackling. If we learn to master the difficulties as extreme as in fusion, we not only solve one crisis, we'll create entirely new possibilities for the generations we won't even live to meet. And maybe the real promise here isn't just a single machine or a single breakthrough, but a reminder that future isn't something we wait for, it's something we build step by step.